Hello, everyone. Before we begin today's event, we'd like to start with a land acknowledgement. The UCLA Samueli School of Engineering acknowledges our presence on the traditional, ancestral, and unceded territory of the Gabrielino Tongva peoples. Hi, everyone. My name is Anjali Koganti. I'm currently a second-year aerospace engineering major from San Diego, California. I'm currently one of two hybrid rocket team leads as a part of a rocket project at UCLA. And in the future, I'd like to work on NASA crewed missions, much like the one our distinguished speaker has been on. So I'm really honored to be here.
And I'm Lindsey Morrill. I'm a fourth-year aerospace engineering major from Orange County and a proud member of the class of 2022. I'm also a rocket project member, acting as the current vice president, as well as doing volunteer outreach at local schools, encouraging students to pursue careers in STEM. After graduation in June, I will be joining SpaceX. I will be working on new spacesuits for future astronauts, as well as the Dragon spacecraft, which our distinguished speaker has piloted. So I'm very excited to be here today.
We're your student co-hosts for this evening's Sugar Speaker Lecture Series. But before we begin, we'd like to introduce our distinguished dean.
Dean Jayathi Murthy holds the Ronald and Valerie Sugar Endowed Deanship here at UCLA Samueli. She's been at the school for nearly 6 years and oversees a class of over 6,500 undergraduate and graduate students, as well as nearly 200 full-time faculty members. In her time at UCLA, she has overseen a focus on growth areas critical to the 21st century, including engineering and medicine and biology, sustainable and resilient urban systems, artificial intelligence, robotics, and advanced materials in manufacturing.
As the first female dean at UCLA Engineering, Dean Murthy has made it a top priority to expand access to a UCLA engineering education. This includes deepening relationships with area community colleges and increasing outreach to groups that are traditionally underrepresented in the fields of engineering and computer science. She also led the effort to establish Women in Engineering, or WE at UCLA, a program that supports the full participation of women in engineering. Dean Murthy is also one of the world's top scholars in the field of heat transfer. She's been elected as a member of the National Academy of Engineering, which is the Hall of Fame for engineers in the United States. Everyone, please join me in giving a warm welcome to Dean Murthy. Now, before we introduce our esteemed speaker for the evening, we'd like to play a short video.
Two, one.
Endeavour launches once again. 4 astronauts from 3 countries on Crew 2, now making their way to the one and only International Space Station.
UCLA School of Engineering, the space station has you loud and clear.
How about that?
Yeah. Now we'd like to introduce our distinguished speaker for the evening. Megan McArthur graduated with her aerospace engineering degree from UCLA in 1993, and she earned her PhD in oceanography from UC San Diego in 2002. Dr. McArthur has been with NASA since 2000, and she's been on 2 space missions. Her first mission was in 2009 aboard Space Shuttle Atlantis to service the Hubble Space Telescope. She was the operator of the shuttle's robotic arm, bringing the telescope into the shuttle's cargo bay and helping astronauts on spacewalks perform critical repairs.
And as if that wasn't enough, nearly 12 years later, she launched into space again, this time as a pilot of the NASA SpaceX Crew 2 4-member mission that launched just last spring. The SpaceX Crew Dragon capsule successfully docked in the International Space Station, where she and her crewmates spent over 6 months conducting scientific experiments and technology demonstrations. But she still managed to snap a few pictures of UCLA from space and share them through her Twitter. In November After 199 days in low Earth orbit and despite a broken toilet, she returned safely to Earth. We are so proud to call Dr. McArthur a fellow Bruin engineer, so please join us in welcoming her and Dean onto the stage.
All right. So welcome, Megan. It's absolutely wonderful and exciting to have you here.
Thank you.
Welcome, all of you. This is our first big event back. I mean, the Ronald and Valerie Sugar speaker series. We've been doing this for some years now, but we've, really wonderful to have you all here back in person. I want to kick this off by thanking Ron and Valerie Sugar for sponsoring this series and for bringing people like you to campus. So thank you. Thank you for being here. Thank you, Lindsey. Thank you, Anjali, for getting us started on this program. And I bet you get this a lot. Welcome back to Earth, to your home planet.
Yes.
So the last time I saw you was in April of last year. I was actually at the Kennedy Space Center launch. I know you didn't see me because you were doing a few things, keeping you busy at that time. And thank you for everything that you've been doing for UCLA. I know you did an interview with a couple of our students. You gave us our commencement address last year, which was hugely well received. So thank you so much for being involved with your alma mater.
Absolutely. Thank you. Very proud to be a Bruin.
All right, so what does it feel like to be back on Earth? You were in, what, 199 days in orbit?
I like to round up. I feel like it was 199 days and maybe 13 hours, so I'm calling it 200. I'm just taking credit for that extra half a day.
Yeah. So what does it feel like to be back?
It's great. I enjoyed my time in space very much. I really got to do so many amazing things, and to look at our planet from space is just remarkable. But I'm very happy to be home with my family. I'm glad to be back on Earth, and I think that it's a beautiful spring weather right now. It's lovely to be here in California. Just feeling the wind on your face, hearing the birds chirping. It's remarkable how that after really missing that for so much time, it can really stop you in your tracks. I was very thrilled to watch my crewmate, my friend, Mark Vandehei, land this morning after 355 days in space. It felt very odd to leave him behind, but I know he's got a little bit of a rough road in front of him. It's hard to get used to 1G again. It's a little bit painful on your body, but you adapt pretty quickly, and now it feels great. I'm happy to be on my home planet.
So I was curious about that. So almost about 200 days in space. What does it feel like? Does it take you a while to get back to walking, or?
Yeah, so we're walking pretty much right away that same day. It's a lot of back pain. So when you're in space, there's a lot of strange things that happen to your body because you're essentially now in free fall for an extended period of time. So one of those things is that your spine stretches out because you no longer have the loading that you have in 1G. So it hurts when it stretches out. It hurts for the first couple of weeks that you're in space, and then it hurts when you come back and it's compressed again. Some other strange things that happen is your brain is remarkable in that it can adapt to the fact that you're falling. That's what you're doing for 6 months, you're falling. And your brain really adapts to that and how you maneuver around in that environment. But when you come home, your brain is a little bit confused again. And so when you make a small movement, your brain expects that your body's going to continue in that direction because that's what's been happening for 6 months. So when that doesn't happen, it's very disorienting. And I felt just very dizzy, right? You feel very uncomfortable, not faint, not like you're going to fall over, but just very dizzy. And so that's like, I went to reach down and grab something out of my suitcase the day after I got home. And the next thing I'm laying on the floor looking up at my husband. And I said, what just happened? And he said, I don't know, you fell over. So it is it's a process for your body to kind of reacclimate to this environment that you've been in, your whole life. So it's a little bit strange, but.
How long does it take?
Everything it's little by little. So that extreme dizziness, maybe 4 days. And it's gradually dissipating over that time. You're driving again after about a week to 10 days. So the docs, check you out and make sure that all your neurovestibular is doing what it should be doing. And then the back pain, probably back pain, and then I had some foot pain just from now I'm walking again, actual like the muscles and bones of my feet were not used to that. That probably took more like 6 weeks or 8 weeks.
Are there longer term effects?
There can be. So there are unusual things that can happen to your optic nerve. You get kind of a wrinkling at the back of your eye, and it's more pronounced in some people than in other people. You can get an increase in pressure and in that nerve. Or around that nerve. And so that can cause vision changes. They can be pretty significant for some people. Folks haven't figured, there's a lot of ongoing research. We had a lot of eye exams, very detailed eye exams, photographs taken of the back of your eye while you're in space. And then when you get home, my effects were milder and have pretty much dissipated, but for some folks that never completely goes away. So there definitely can be things that last for a long time.
Wow, these are the things that you don't hear about. It's very interesting. So you were the pilot of the Crew 2 mission. What does being pilot involve?
So there are 4 members of the crew for a fully staffed vehicle. I'll say that the original mission just had 2 because as a test mission, you want to go with kind of a minimum crew. There were 4 of us on our mission, and the commander sat to my left, and then I had a mission specialist to my right, and he had a mission specialist to his left. And so the commander and I share 3 screens between us, and we are mostly monitoring the vehicle. The vehicle is designed to be, it's a combination of being autonomous, meaning it's making decisions for itself, and then it's receiving ground commands from the controllers in Hawthorne. And we have some limited insight and limited capability to send commands, but most of that's being done, from the ground and by the vehicle itself. And so we're monitoring systems. And so my role as the pilot, because it's so new, we're kind of inventing our own roles. And so I took from a shuttle model, the pilot's job is to really monitor all the spacecraft systems. And so understanding, what's going on with the electrical power system, what's going on with the thermal control system, understanding how those systems are built. And then, when we potentially get a malfunction, hopefully only in training do you see malfunctions, but what is causing that and what is the impact? And so I kind of took it upon myself to want to be able to tell the commander something about a failure, maybe before the ground called up. So he had some information before we were getting the full story from the ground. And so in my mind, the pilot's job was to just kind of be the systems expert for the vehicle.
How long do you train for these kinds of missions?
So we trained for about 9 months. Typically for a space station mission, you're going to train for 20 months. And that's because of the detailed activities that you're going to be doing in space, more so than for the vehicle itself. In our case, because of the nature of the development program, there was some uncertainty between when we would actually launch. And so we got assigned pretty late, and it turned out we launched about a year after we were assigned. The training flow itself for just the vehicle could certainly fit into 9 or even in 6 months, but you're trying to fit that in amongst all of the other training that you're doing for a space station.
Now, this all happened during COVID. So were you all hermetically sealed from other human beings? I mean, how did this all happen?
So that was a real challenge. We were the first crew to completely train and fly and return, during these COVID restrictions. So the teams between NASA and SpaceX really pulled together. We're very creative with how we could continue that training and keep everybody safe, not just the crew that's going to fly in space, but of course the instructors as well, and all of our families, right? So minimizing that exposure. So really minimizing the number of people that had to be at any given training event. For our robotics training, we typically would sit in a very small room with 1 or maybe even 2 instructors when we're going through different training events. And they ended up coming up with a way to do that remotely and we had two training rooms that are adjacent to one another, but no connections. And so your instructor would be in one room, doors closed, its own ventilation system, you're in a different room, and then we would do teams. And so they were able to pull up all of the displays in the second training room and watch what I was doing and be able to provide me feedback that way. So that's just one example of sort of being very clever about how we do things. We traveled out here to Hawthorne frequently for our training, and SpaceX had, the training center pretty much sealed off. We had a separate entrance. Only people that were required for training were allowed in the facility. Everybody was tested every day if they were interacting with us. So they took it very, very seriously, and we felt, very safe throughout that process.
Quite the journey, very different from other trainings, I would imagine. So how do you prep for emergencies? I mean, I'm very curious about, there's risks all along, particularly at takeoff and so on, but also on the space station itself.
Of course. So yeah, living in space has some significant risks associated with not just the ascent and entry part of it, as you alluded to, but also living actually in this enclosed environment where you've brought everything that you need, your atmosphere obviously being very important to you. So the big things that are considered emergencies in space, of course, would be a depressurization. If you had, some debris that knocked into the space station and put a hole in your vehicle and you start losing your atmosphere, that's an emergency that we train to respond to. A toxic atmosphere would also be equally bad. We have ammonia in our external cooling loops, and there is a specific failure that could cause a breach of that ammonia gas into the atmosphere of the space station, which would be a very critical emergency. And then of course, fire. So we train for all of those specific emergencies over and over again. We train individually so that we know the equipment and we know the procedures by ourselves. And then we train together as a US, what we call the US operating segment crew. And then we train as well with our cosmonaut crewmates. We did see a variety of, I won't say emergencies, we didn't have any actual emergencies, but we did have a warning class events, which are kind of considered, you have a little bit more time to deal with a potentially life-threatening situation, or it's a hardware threatening situation. We had smoke alarms going off in the middle of the night one night and having to enact the fire response. So you've done it so many times that your training really just kicks in, and you go immediately where you need to go. You gather up in your teams. Those are the only hard copy procedures that we have. Everything else is electronic. You get the book out, you start flipping through pages, you're calling the ground, you're making sure that they're there to help you. If they're not there to help you, then you're on your own. But yeah, it's just a lot of practice, a lot of muscle memory to remember those things.
I seem to remember that you'll have to suit up, right? I mean, there was something about space debris
memory,
or
yes.
something.
Yes, so while we were still in the Dragon capsule, so it took us 23 hours from launch to all the way to rendezvous with the space station. So 23 hours just in the capsule. And the first night, the night that we spent on orbit, we had just gotten all of our sleeping gear out, our sleeping bags, we've gotten into our pajamas, we brushed our teeth. So everything is out in the capsule. And we get a call from the core, the ground controller who speaks to us from the Hawthorne Control Center. And she said, we're tracking a piece of orbital debris. It's predicted closest approach is within that, that red box that we monitor, and we need you in your spacesuits right now. You have 20 minutes. And so, so then it's, a flail basically you've got to get out of your sleeping bag, out of your pajamas, into your spacesuit. There's 4 of you. All of that stuff that you've just pulled out of these tiny little compartments has to get put back away, because if you do have to do an emergency deorbit, your center of gravity has to be a well-known condition so that you can land safely. So every bit of material that we've gotten out has to go back. So the way we handled that was the commander and pilot, we got into our spacesuits first with the help of our mission specialists. Then they helped each other get into their spacesuits, and then they put everything away while we started monitoring, the vehicle systems. And then as soon as everybody got in their seat and buckled in and strapped into their umbilical, the ground called us and said, that was a false alarm. You can go back to sleep now. And of course, everybody's heart, is racing at that point. So
back into your pajamas.
Back all the way back out. Yeah. So that was, we felt like, so we have a person when we're training called the simulation supervisor, we call him Sim Soup. And so we're like, nice one, Sim Soup, because that's the kind of thing that would happen in training where they would, throw the book at you, if you will, and then say, okay, now that one's over, we're going to do something else to you next. And so it felt very much like a simulation, except that we were all floating.
So what's the feeling? I mean, when you're blasting off, is it fear? Is it excitement? Is it impatience? I mean, what do you actually feel?
So it's a lot of excitement. So when you're waiting, there's a little bit of impatience, maybe, but it's excitement. It's really excitement. There is a couple of hours where you're sitting strapped into your seat and just waiting for the tanking to happen. The fuel gets loaded onto the vehicle, and so there is a little bit of impatience, and you kind of have time to kill. So some of that time we spent, of course, being serious professionals that we are, we reviewed some of our emergency procedures. We talked through different anomalies that might happen, and then we played games. So to pass the time. So that was fun. And then when we actually launched, there was definitely some hooting and laughing amongst the crew. Once the commander started giggling, I figured I was in the clear to start laughing a little bit, and we all, were kind of high-fiving each other and fist bumps and everything, just enjoying the ride. It was a tremendous day.
I mean, it was huge fun being at the launch. I mean, just watching you guys take off was really, really exciting. So tell me a bit about the Hubble work that you did. So you would have heard today, right, that Hubble took a picture of the farthest star that it's ever taken. And this isn't really just a blurry galaxy picture either. This is actually of a star that's now supposed to be, 28 billion light years away. But you were a part of a repair crew that actually went and fixed things.
Yeah, so in 2009, I went with a shuttle crew on the Space Shuttle Atlantis to the rendezvous with the Hubble Space Telescope. So it's been in orbit now for over 30 years. And of course, it wasn't originally designed to be in space that long, but we were able to do a repair and upgrade mission. Some of its most highly used science instruments were broken. And so rather than just get rid of them or replace them with something else, they ended up designing a way for us to do an in-space repair on a computer, essentially, that had never been designed to be repaired in space. Now, we build a lot of things to take apart in space during a spacewalk, and they have a very specific kind of structure and a very specific kind of design, and big bolts that can be used, that we can remove with a specific tool that we have. Well, this was none of those things. It had, to get at the computer boards that needed to be changed out, we had to remove a panel that had over 100 non-captive torque set fasteners, really tiny ones. And so you can imagine that if you lose even one of those fasteners inside the telescope, you've pretty much ruined the telescope. And so the engineers came up with an ingenious solution, which was to put a clear plate, bolt a clear plate over top of this panel with slots drilled into it that you could then put a drill bit through and back the screw out. So then it was captive between the plate on the computer and the plate that you had just installed. And of course, you need to do that without stripping any of the screw heads. It was very, very complicated process. And that was just one of the spacewalks that our crew did. So I was the robotic arm operator for that mission. I got to grab the telescope after we had rendezvoused with it and place it in the payload bay. And then during all the spacewalks, when we're moving large pieces of equipment around and people, then I'm driving the robotic arm to put them in position for that work. So that was tremendous. And I love that I got to be a part of that, because then even all these years later, when there's a discovery like that, I go, oh yeah, I did that. That was, you're welcome. So I'm not an astronomer at all. I'm not an astrophysicist, but it's really amazing to be part of something like that, that's bigger than yourself, that people around the world benefit from, and will be, it's part of history. So it's really special.
Yeah, I mean, Hubble's been phenomenal, and now James Webb is off and running.
Yes.
So this is a high exciting time
Absolutely.
for astronomy and everything else. So this seems like an extraordinarily long way from being a UCLA Samueli engineering student. I mean, this is really phenomenal. I'd like to, explore a bit about your own personal life. I mean, why did you choose to come to UCLA? Why mechanical and aerospace? What drove those decisions?
Sure. So my father was a pilot in the Navy. My sister is here as well. So she and I grew up moving around the world to different air stations around the world. And our dad would take us to air shows and sometimes air museums. And so I had a love for airplanes early on. And we lived at an air base in Northern California called Moffett Field Naval Air Station, and which is no longer in existence. The runways are still there, but there's a NASA center there. And I would see, as a high school student, I would see NASA astronauts come in their T-38 jets and get out of the jet and come in to use the landing simulator for the space shuttle. This was in the mid to late 80s. And I thought, oh, that looks like a pretty cool job. How do I get a job like that? And knowing that it would be a long shot to ever be an astronaut, I thought, well, I still want to be an engineer. I still want to work for NASA. I didn't have any engineers in my family. I didn't really know what that meant, but I knew that I wanted to be part of something that had these big goals, right? That had these kind of almost outrageous goals, really, when you think about it. When I watch launches, I think, that's outrageous. Who does that? It really is wonderful to be a part of something like that, that takes so many people together to accomplish it. And the challenges are always different. You're not doing just one thing, you're having to do lots and lots of different things. So that was kind of the original idea that I had. And of course, looking around at the schools, UCLA was the best aerospace engineering school that I could find. And I wanted to come here. And I was lucky enough to get in. And the experience of going to school here was, it was fantastic. You know, the faculty has been amazing. It's a big school, but you still have faculty that really care about you doing well. Which I think is really remarkable. And I think the formative experience for me here was being part of a team that chose to do an engineering competition. So this was the human-powered submarine races, which I don't think exists as a team anymore at UCLA, but there's the human-powered vehicle, there's the cement boat, there's all these different cool engineering projects, right? And so getting to work together on a team was the formative experience that I had here. Understanding that your contribution might have to change, right? You're gonna do the job you were given, but then you might have to do somebody else's job. You do everything with a project like that. You're doing the fundraising, you're doing the design, you're doing the building, you're staying up all night. You know, I fell asleep one time in a chair outside the lab. I was just exhausted. We've been working for days, you know, trying to get the sub ready for the races. And I fell asleep, and then I woke up a little while later, and I felt kind of funny, and I was doing this, and you know, a couple hours go by after doing some more work, and then I go into the restroom and I see that the rest of the team had drawn all over my face because I had dared to fall asleep while there was still work to be done. So that's an important lesson too, that, you know, nobody sleeps on the team until all the work is done. And, you know, those were the experiences that I had at UCLA that, I mean, frankly, changed my life, really set me on the course to where I am right now. Was that team project, that experience of working really hard on a goal together. I learned a lot from that.
Yeah, we've got lots of students here who belong to clubs, and particularly the Rocket Club and Rocket Project, and they bring the same kind of passion and the same kind of interest there. And I know that you guys all missed this during COVID, and I'm so glad to have you all back and doing all that fun stuff again.
Don't fall asleep.
Yeah, don't fall asleep, or you'll have stuff drawn on your faces, I guess. So tell me, so after an MAE degree, you went off to get a PhD in oceanography. What drove that, and how does that connect to going back to becoming an astronaut?
It's a good question. So so the part of that project, the human-powered submarines were actually flooded. So it was not a pressurized vehicle, because that's a whole nother level of complexity, right? So they're flooded, and so the people operating it have to be scuba certified. And so I was the smallest person on the team, so I was designated the pilot, because we designed most of the space to be for our propulsive guy, right, who was this big guy from the UCLA triathlon team, and so the space left over for me was pretty small. So so I had to get scuba certified. Not a swimmer. I mean, I could swim, but not a strong swimmer, not an ocean lover, not someone that spent a lot of time in the water. So it was a real significant challenge for me. I struggled with that. I found some help here at UCLA. There used to be a dive safety program. I don't know if that still exists, but there was a dive safety program. And so they really helped me. And in the process of doing that, I felt like I had really achieved something. And I really kind of fell in love with the oceans in the process. And so I thought about, you know, ocean exploration as kind of a new goal. And for me, there's a lot of similarities. You know, our planet is over 70% oceans, and there's still a lot that we don't know about the oceans. And in order to explore them, we have to use technology in ways similar to how we explore space, right? We don't survive underwater any better than we do in outer space without special equipment. So there was a lot of parallels. There was enough for me that I felt like I could make this turn, I could explore this area, and I know enough that I can contribute. I was speaking with a young man over here about how I kind of made this switch into signal processing, and not having a background in electrical engineering, there was a steep learning curve there. But I knew enough. My engineering education, you know, you train your brain here at UCLA, right, to solve problems and to learn, you know, to take in a lot of information, right, and to learn quickly, drinking from the fire hose, right. I know you guys are all doing that in your classes. But I knew that I kind of kept hold of the idea of, I would love to work for NASA one day. I'd love to fly in space one day. But I did struggle with that decision. And I had the opportunity when I went to the submarine races, I met an astronaut named Kathy Sullivan. Her picture was up here earlier. She was the first American woman to do a spacewalk. And so I had this opportunity to talk to her, and I said, you know, what do I do? Here's my dilemma. What do I do? And she said, you know, you can't choose what you're studying based on what you think NASA might want, you know, years from now. You have to choose based on what you love and what inspires you. Because if you choose something that you don't love, you're never going to be good at it. And if you're not good at it, they're never going to choose you anyway. And the chances that you get chosen are pretty small. So you want to choose something that you love, you're going to excel at it, and you're going to always love your job rather than trying to figure out what somebody else might want. And so I took that advice and I ran with it. And it ended up working out really well for me. I got a great education at Scripps, a lot of what we call operational experience. So working on a ship, deploying and recovering instruments, scuba diving and deploying and recovering instruments, as well as doing the theoretical work. Again, working as part of a team. All of those valuable skills that I started here, was able to grow them at UC San Diego. And so then when I applied, I got really lucky and got selected. So,
well, tell us about that. I mean, how do you get selected to be an astronaut? I'm assuming that that's not a follow-on career for engineering deans, but I'm hopeful that it might.
You never know that the career field is expanding as we speak. So, so I've actually been on the selection board a couple of times, so I've gotten to see it from both sides of the table, which is great. And it has changed a little bit over the years as we've changed our goals. The kinds of people that we look for change. We used to select maybe a lot more independent operators. Shuttle missions were short. And so now with 6 months missions to the International Space Station, you really, really need those team skills. And so that part is really important. And so a lot of what we're looking for after all of the credentials is this somebody that I want to live in a very small environment with for 6 months? But we get 18,000 applications for maybe about a dozen positions at any given time. And so what we're looking for are people with science, technology backgrounds, also operational backgrounds I kind of alluded to with working on a ship, but some situation where you are, maybe you're flying an aircraft, or maybe you operate a race car in your spare time, some situation where you are operating, doing something technical and potentially dangerous situations. So the ability to do things methodically, even when the situation is potentially dangerous. But also just hands-on mechanical skills. So maybe you like to repair race cars, or maybe you're building rockets. Those kinds of things are very highly valuable skills as well. A lot of what we do in space is we're doing maintenance on a space station that's been in space for 20 years. And so you get a checklist that you've never seen before. You are working on a piece of hardware that maybe you've never seen before. You're taking it apart, you're giving it some kind of upgrade. And so you need to be familiar with tools. You need to be able to run methodical procedures. And you need to be able to communicate with people who are not in the same room with you about those things that you're doing. So any way that you can develop those skills, I think those are the kinds of things that we're looking for. And it runs a pretty big spectrum.
Boy, I mean, that is a whole lot more selective than even getting into UCLA engineering. So, yeah.
No, it might be close.
Yeah, close, only a couple of decimal places off. So I want to talk to you about being a woman engineer and a trailblazer. Really, it's phenomenal to see you up there. It's extraordinarily inspiring for all of us. Do you have any advice for our women engineers? What should they be thinking about? How do they pursue technical careers at NASA? What if they wanted to be an astronaut?
Absolutely. So I would say, go for it. That's the bottom line of my advice is go for it. I've been at NASA for 20 years. I've seen changes over that period of time, but I can tell you that right now, NASA is looking for people of any gender who are inspired, who are motivated, who are hardworking, who are ready to bring their complete authentic selves to work every day and work on these, amazing missions that we're getting to do. We're going to be putting people on the moon. Again, we're going to be sending people to Mars. In the times that I have worked at NASA, I started off where, and not at Johnson, but when I was an intern while I was here at UCLA, I had an internship at one of the NASA centers. And I remember being the only woman in the entire department. And there would be times when I would walk into a situation, maybe we were going to be doing a test on an aircraft, and the conversation would stop and literally everyone would turn and look at me. And this is not, I'm not the bride. I don't want everybody looking at me. This is not a comfortable situation. And we have grown so much since then to where, I have women at every level of leadership in my organization. I have a seat at the table. And so I think that's so important. We spent the morning at SpaceX today, and you see that there as well. One mark of that I have seen is, when I first started working in mission control, one of the jobs that astronauts do in mission control is what's called the capsule communicator, or Capcom. And we work, whenever the crew is awake, we're awake. So there's some middle of the night shifts that you're working. And when I first started working, you get a 2-minute break when satellites hand over from one to another. And so everybody rushes for the restroom, right? And so you rush out the doors. And at that time, when I first started working, there were 3 restrooms on the whole floor, and I could have a whole women's restroom. It was like having my own executive washroom. There was no one else there. There would maybe be 3 women in the control center, the whole building, and we'd each get our own place. You know, nowadays you go in at 2 a.m. and there'll be a line for every ladies' room, just like there is for every men's room. So that is a mark of progress in the number, just the sheer numbers that we have, and that's because the representation is happening at this level, right? It doesn't come to the workforce level until it's happening here. And so the work that you're doing here to make that happen, I think, is really tremendous. So. I think it's a welcoming environment. I have tremendous women leaders in my life, mentors for me, and people that I look to, and we are all standing on the shoulders of giants that came before us, and it's our job to boost up the next generation. So find a mentor. That mentor doesn't have to look like you; they just have to believe in you. And then I would say, be a mentor. You have the opportunity to help the people that are coming up with you. And you have a responsibility to do that. Help each other, share your goals with one another, and help one another along the way.
Wonderful. Now, the International Space Station is going to be retired in what, 9 years?
Something like that.
What happens next? I mean, what happens to it? Are there other space stations planned? I know China's got one up there.
Mm-hmm. Yeah. So the space station's been in orbit for over 20 years, as you probably know. So that's probably a lifetime for some of you. The structure itself, of course, is going to have degradation over time. And so we've been able to predict, through analysis, how long we think the various structures will last and be safe. And so the things that cause the degradation, you get dynamic events, dynamic loading events of the whole structure. So the truss structure, which is kind of the backbone, and all of the individual large segments. So spacecraft dockings and undockings are causing dynamic loading on that overall structure. And then thermal cycling, right? So we go around the Earth every 90 minutes. You're going through a sunrise and sunset, and there's temperature extremes that all of that hardware goes through. So over time, you're going to get degradation of those structures. And so the prediction is that we can safely operate through 2030, and then after that, the space station will be deorbited. And so in order to do that, we'll use a combination of sort of the natural decay from the drag of Earth's atmosphere, as well as then an actual deboost burn. Mm-hmm. And the space station will start, based on what we know from other space stations like Mir that have done that previously, the big pieces like the solar arrays and the radiators will come off first. And then the individual modules will, sort of melt from the outside in. There'll probably be some pieces that are left over that will splash down in the ocean. I don't know on what scale that will be, but they target a spot that's the farthest away, the point that's farthest away from any piece of land. And so that's what the plan is. That's the level of detail that I understand at this point. So following that, we do have partnerships with different commercial organizations to either send a commercial module to the existing space station, and then they could potentially undock before this deorbit happens, with the idea that there would then be commercially operating space stations. And so NASA's plan would be that we would purchase the services that we need from these commercially operating space stations. So we could continue to sponsor scientific research from universities and that kind of thing. But these commercial entities could also be a clearing ground for people to come and to do their research or to do their manufacturing, or maybe there'll be a hotel in space and you could have intrepid travelers that go into space for their vacation. I don't know exactly what that market will look like, but that's the intent. And then NASA would use its resources to focus on the exploration missions like Moon and Mars.
Mm-hmm. Wonderful. So what's next for you, Megan?
Good question. That it is a really good question. So it's something I think about a lot. We do get some time when we get home. We first will, of course, do a lot of medical studies. They want to know what's happened to us while we're in space, and we do a lot of debriefs. We give a lot of feedback about the mission and how things can be better. And then we get some time to kind of recuperate and reconnect with our families. So I think, when I look back, I don't feel like I have missed something. I have had an amazing time living and working in space, and I don't feel like there's something missing. And we have a lot of young, new astronauts that are ready to come up and to fill the roles. We're sending people to the moon. I would love to go to the moon, but having been through with my family a development program already, the commercial crew program that developed the Crew Dragon and the Boeing vehicle, that takes a toll. It's a long process, and it takes a toll on your family. You kind of mold your life around that business for many, many years. And of course, we have the reward of some amazing, spaceflight opportunities, but it's hard to keep doing that. And so I think I will look for a support role in some fashion. I mean, never say never. Maybe 10 years from now, I'll say, no, I'm ready to go back and I'll be one of these commercial flyers. But for now, I'm happy to be on Earth and enjoy Earth. I'll probably do some camping this summer with my family and just enjoy the beautiful planet that we have. But I will say, if any of you end up going to Mars, I hope you will send me an invitation, and I will lead the 8 clap from the stands and cheer you on.
Hey, you come teach at UCLA. That's always open. We'd love to have you here.
Great.
All right, so I want to open up, our gathering here for questions. I know all of you've got a whole bunch of things you want to ask Megan. So let's get started.
Please hold on.
Oh.
Hi. Can you talk a little bit about the differences between operating in space and being in mission control and sitting on console, and what's it like in those different environments?
Absolutely. So the Mission Control Center is in control of what's happening on the space station. I like to say the flight director is actually the boss. It's not the commander that's in space. Now that changes if there's an emergency, and then the on-scene team, of course, is in charge. But the ground team, and there's ground teams around the world that are coordinating all of our activities, whether it's science activities or maintenance or what have you. And so they plan our every move for every day. And then we enact the plan. And so when things don't go according to plan, we check in with the ground, and they either provide us immediate direction or they have to go off and think about it. And because you're the person that's on site, it's your eyes and your brain and your ears and your hands that are right there. They're really going to heavily weight what you say and what you suggest, but they're going to work with the team that they have on the ground to try to come up with solutions. So does that kind of answer your question? Does that give you some sense of? Okay.
Thank you. Is there a different feeling being like working a problem on the ground versus space?
That's a good question. So the question was, is there a different feeling working a problem on the ground versus working in space? And I would say that the time urgency is kind of the thing that can make a difference. So, and that doesn't change. So if there's urgency in space, you behave a certain way, just like you would on the ground if there's urgency. If there's not urgency, then you rely on the ground team to solve that. Now, the practical aspects of working in space, often involving tools, right? Keeping track of your stuff is a real serious problem, right? I mean, there's nowhere to put it down. So everything has to be Velcroed all the time. And you are going to, even if you think, oh, I've got a system, I have a plan, you're going to lose something. And someone else is going to find it and tease you about it. So it's just part of the process. No, we all look out for each other, but that's probably one of the most noticeable differences, is that you can keep track of your stuff pretty well when you're on Earth, and it's really, really hard to do in space. Mm-hmm. Oh, I'm sorry. I think they want to get a microphone to you so everyone online can hear it.
So I was wondering about just like internet in space, what it's like using that to connect with your family back at home, and like maybe how much of latency there is there, and maybe doing experiments that you don't really have a lot of knowledge of, and so you can look up things.
Sure. Yeah, 2 great questions. So we only recently got internet access. So we have connectivity with the mission control centers, but only recently did they create a system where you could actually surf the internet on your own and look up whatever you wanted. And the way they do that is by routing it through a server on the ground, so they can completely isolate. So you can't, accidentally get a virus on board the space station. Now we have 2 completely different systems. Obviously, one that runs the space station, and one that's just what they call the crew personal. And so there isn't even a crossover there, but for that extra level of caution, we go through a server on the ground. So it's slow. You have access to email on the primary server, so that's actually pretty quick. You have over the years, so it used to be in the beginning, you get like 1 email uplink per day. Now we have continuous connectivity with your email all day. We also have an internet protocol phone, so I can pick up the phone and call people here on Earth, as long as we have the right kind of satellite coverage, which is wonderful. And then we get a weekly video conference that they set up through the Mission Control Center, so you can have a live video chat with your family, which is great. And it is very helpful actually to be able to look up information about science experiments that you might be doing. People hear about experiments that are going on space station and they automatically think you're an expert in it. And my involvement with a given experiment might be, pretty minimal. So we can be extremely hands-on and very involved in the experiment, but we can also be just changing out media cartridges kind of thing. And so being able to understand what I'm doing and then also be able to explain it to people, I would definitely use the internet for that, for sure. Yeah. Microphone's coming your way.
Okay, I'll jump in next. So first, from the online audience, Megan, I want you to know that Bondo boy Brian Clark from the Human Powered Submarine Project and Tom Weir, you've got a lot of classmates in the chat, and even Travis from Delta Sigma Phi. So
wow.
There's a lot of love in the chat. But an actual question from the Q&A.
Bondo boy, oh my gosh, that's fantastic.
Is from Mike. I know you talked a little bit about the physical effects, but Mike wants to know how you manage your sleeping schedule when you were in space going around the globe.
So the ground manages all of our schedule, and they schedule a sleep period for you. And so we operate on Greenwich Mean Time, which is roughly the equivalent to the time it is in London. And that's kind of a middle ground between the different international centers that we have around the world. And so we typically, we start our day officially with ground control in Houston, 7 a.m. on our clock. It's about midnight on Houston's time. And then we end our day with another meeting at 7 p.m. Our time. And so then you've got a couple of hours to sort of do whatever you want. And then the sleep period is scheduled for 8.5 hours. Now you're not required to sleep at that time, but that's the time that you're given, protected time to sleep. You get your own little closet basically to sleep in, where you have your personal laptop. You can put family photos up on the wall. Your sleeping bag is in there. And it's actually reasonably quiet for the amount of noise that exists on space station. It's a reasonably quiet little haven. No window though, which would be nice, but no window.
Hi, I was curious to know how your graduate degree in oceanography influenced your work at NASA, and I mean, if it influenced, your work as an astronaut.
So I would say the experiences are more about the skills that I developed there rather than the research in particular. So I don't do oceanographic research from the space station, although people do use different pictures taken by crews to look at different features on the Earth and on the ocean. But it's more the skills that I gained. Partly, we talked about as an engineer, you're sort of learning to drink from the fire hose. You're learning sort of new topics all the time and assimilating a lot of information. A graduate degree is very similar to that. You're becoming an expert in something, and you're doing that relatively quickly. And so just that experience of onboarding all that information is part of it. And then the experience, I would say, of working at sea, working with a team, working underwater with hardware, all of those skills translate in a lot of ways to the kind of work that we do in space. Yeah.
I'm a high school student at Geffen Academy. My question was, what was the most interesting experiment you did on the International Space Station?
That's a great question. We do a lot of really interesting experiments. So not a biologist, I'm an engineer, like most of you. And so the biology experiments were a little bit intimidating sometimes. And it'd been a long time since I'd done any pipetting. So we had an interesting experiment called celestial immunity that involved getting donor samples, blood samples into space. We were centrifuging them and then, creating samples by adding different materials to them and then incubating them and then examining them. I talked about how difficult it is to manipulate all of your tools and not lose track of things. And so now consider that I'm in a glove box, right, to maintain all of these fluids inside a controlled environment. And everything in there has to be, taped down or Velcroed down, and you have to keep track of everything. And these are open wells of different, very important samples, right? And not wanting to spill any of that. So So that was a really interesting experiment. Just from an operational perspective, it was very intensive. I had an expert on the ground who was, camera over my shoulder, watching my every move. If I had a question or if I missed a step, she could call me on it, because of course my hands are in this glove box. I don't have any way to page through a procedure. So she's talking me through it step by step. And then it's also interesting for the science that it's actually studying. So your immune system can get a little bit wonky in space. And so people study why that is. But one of the things that means is that it's a kind of an accelerated environment for studying things that might also be happening on Earth. And so we can try different treatments and you get an accelerated response in space that then may help you develop, may give those returns back for Earth in a more accelerated way. Similar with muscle loss. So we experience muscle loss at an accelerated rate. So we did an experiment with engineered muscle tissue where they could look and see, is this engineered muscle tissue responding in the same way that muscle tissue would respond, real muscle tissue would respond? And then to this sarcopenia effect, this muscle loss effect, is it showing the same kind of genetic markers and those kinds of things? So a lot of really interesting, detailed studies are ongoing. And these studies, of course, take years to get the actual results. So I'll have to be kind of listening out for, when the papers get written. But it's pretty neat to be a part of something like that as an ongoing study. Yeah.
Hi. My question is, what was the most challenging thing that you had to go through throughout your career studying and getting to be an astronaut? And how does balancing it with your family life factor into that? Was that the most challenging? And if you can elaborate more on that. Thank you.
So oftentimes the most challenging thing is just the sheer volume of different things, but it's also what is the most appealing about it to me, right? So managing all of those different streams of information and being able to kind of code switch from one thing to another, especially in space, you'll be working on one experiment, maybe it doesn't go well, your time has run out, now you've got to go and work on something else. So that ability to switch rapidly from one thing to another and make progress, right, in all of those areas, that's a challenging thing. Physically challenging, the most physically challenging thing, I think, for astronauts is learning to spacewalk. We have to learn on Earth, right? So you're still experiencing the effects of living in 1G. Spacesuits are really, really heavy. They weigh hundreds of pounds. We do that training in a giant swimming pool that can alleviate some of that load, but not completely. You're still having to move this large mass around. So it's physically exhausting. The suits maybe don't fit all that well. The work that you're doing is difficult. You might be upside down, so blood is rushing to your head, which of course would not be a factor in space. So a lot of, it's physically very challenging, very demanding. It's physically demanding in space as well, but for kind of different reasons. So those are some of the challenges. Certainly having a family, having a young child is challenging as well, with my husband flying in space and then coming back and then me flying in space. But you have a good support network. We had a wonderful babysitter that just really, I told her the other day, I said, just keep our family running. So you have to look for that help for those kinds of things and ask for help when you need it.
Hi.
Somebody way back.
Hi. So first of all, you're amazing. I snuck out of work to come see you.
Have your boss call me if there's a problem.
So as I understand it, the Hubble today viewed the most distant star that we've ever seen. And I'm sure the JWST will also find more discoveries like this. What do you think we might find out there? How can we prepare for that?
That's a fantastic question. So one of the things I think is amazing about the Hubble Space Telescope is that it was designed to answer some very specific questions about the universe, but it has already found so many more answers to questions we weren't even smart enough to ask. So your question is kind of impossible to answer, right? First of all, not an astronomer. We design these instruments to answer specific questions, but we're going to learn so much more than that. I was reading today that we might be able to detect methane with the James Webb Space Telescope, and then we have to figure out, is that the kind of methane that would be produced by life? So just kind of even thinking about these questions, we get smarter all the time. So I think we're going to be astonished for years to come, which I think is fantastic. That's why we do these things.
Hi, so now we've been seeing that there's a lot of more commercial ventures into space. It's not just like NASA as it was decades ago. So how do you see the landscape of space travel changing and some of the risks and difficulties with making that transition to a commercial enterprise?
Sure. So yeah, you are right that we've already seen a lot of changes with our commercial partnerships. So NASA intentionally has been working for at least 10 years to foster an economy in low Earth orbit, right? And so some of that started with partnering with SpaceX back in, I think, 2006, with them to develop a commercial cargo vehicle, so an uncrewed cargo vehicle that goes to the space station. This was, knowing that the space shuttles were going to retire, we were going to need a way to get cargo to and from. And so this has, been planned out for many years to try to, hand over some of these things to commercial entities and help them become profitable and have this sustainable economy. So I think, we might see things like potentially manufacturing in space of materials or medicines that are going to, I'll say, grow differently in a zero G or micro G environment than they would on Earth. So maybe there's a market for that kind of thing. I do think there will be a market for, some level of tourism. We're already seeing that kind of thing. We had an actor and a producer come to the space station on the Russian side while I was there to film a movie. So those kinds of things will be, interesting to people. And then it will build. I was joking with some crewmates. We had an impromptu Summer Olympics on board the space station that was a lot of fun. And so I think about, what kind of artistic performances could you do, if you had a big space up in orbit. So I think, again, we almost can't guess what that is going to look like, but it will be good to be fostering that economy so that the government can focus its resources on doing kind of the bigger, more risky projects. As we learn how to do something nearby, it's kind of like expanding across the US back in the day, right? The government doesn't need to stay involved at all of those different roles. But spaceflight is risky, right? It's going to remain dangerous. And so there are risks and costs associated with that. So you just have to be very careful about how you move forward, make sure that right kind of regulation is there. Even to something as maybe mundane sounding as how much orbital debris are we leaving behind, right? That's going to cause problems for other things that are in space. So lots of questions to answer, and figuring out, does that take government regulation or can the private sector do that itself, will be interesting to see how that unfolds.
Okay, second to last question over here.
Hello, I was wondering if you could talk a little bit about your first time looking down at Earth from space and kind of what went through your head.
So the very first time would have been on my shuttle mission to the Hubble Space Telescope. And when you first get on orbit, you've just had the most amazing, Mr. Toad's wild ride times a million. You're just rocking and rolling and shaking, and you're like a rag doll. And so when you get into space, you're kind of relieved, like, wow, I just made it through. That was amazing. But then you immediately get to work turning your launching vehicle into an orbiting vehicle. The space shuttles were built, designed and built in the late 70s, early 80s. And so the technology was such that you have to reload your whole computer system, all your software, as soon as you get into orbit to be a completely different set of software. So your head's down in a book for hours, right, when you get on orbit. And so I remember looking out the window and going, okay, Earth, that's right where it's supposed to be. Good, back to work. And not really having any time to take it in. And it wasn't until I really had time to look out the window while I was doing some robotic operations and see, lightning over the surface of the Earth, I think over the oceans on this huge scale, kind of different colors, and it flashes on and off, and you can see the whole thing, and it was mesmerizing. And you really realize this is a living system. This is not a static photo like what I'm used to having seen growing up. I've seen all these photos. This is a real living system. And seeing the atmosphere, seeing this very thin, you can't even imagine how thin it looks to you when you see like this vast blackness of space and the big blue Earth and this teeny tiny atmosphere that's keeping all of us alive down here. It's a visceral response. It's this very protective urge, like, oh, we gotta do it right. This is the best planet that we know of, and we gotta take care of this one. We talk about terraforming Mars, we're going to Mars, but we need to take care of the planet that we have, and that's planet Earth. So those were the feelings that I had. And every time I look out the window, even so, those are the feelings that I have.
And you can confirm that the Earth is not flat. Right?
I can confirm the Earth is not flat.
There you go. Eyewitness, guys.
Hello. So earlier you mentioned that experiments like mine not just succeed. So how often does that happen? And like what proportion of experiments like do not succeed? And I was also wondering, so you were mentioning like the effects on the brain. So are there like neuroscience experiments that are that happen in the ISS?
Absolutely. So two great questions. So I don't have a number for, you know, what proportion of experiments don't succeed. We used to spend a lot of time trying to vet experiments before we even allowed them to fly in space. And now we have taken a different tack to try to get as many experiments up there as we can, expecting that there's going to be some amount of, I'll say, failure. Now, you always learn from failure, right? You know that as an engineer, you're always going to learn something, and you're going to be able to turn it around and do make improvements, right? And so there is some proportion. I don't know what that number is. We try to spend the time that we're given to make things work when they're not working. And we have a lot of experience right now. We have some ideas of what does work. The interesting thing is, as you get different commercial companies privately doing different things, and maybe there's not as much information sharing, there might be one group that's gotten really good at doing something and another group that's trying to figure it out, and they may or may not be able to share some of that proprietary information. So that's interesting. Second part of your question about neuroscience, absolutely, we do neuroscience experiments. One very basic one that we do regularly is to just kind of see, you know, what kinds of effects that living in space is going to have on your brain from a, you know, timing response kind of thing, the ability to do simple mathematical functions. And so you go through this battery of tests. You start doing it 6 months before your launch, and then you do it every month while you're in space, and then you do it again while you're home, and they look at, you know, your performance in these different battery of tests. Some of them are more complicated than others, and you could always tell when somebody was going through some of it. You know, there might be some complaining coming out of one of the modules when someone was having to go through one of the really challenging ones. But it's interesting to see, and you could sometimes tell, and you're supposed to make remarks like if maybe you didn't sleep well for a couple days before the test. You could kind of tell, like, ooh, yeah, I did not do so well on those tests today, and you kind of, you know, not that you were required to, but, you know, I might say to my commander, ooh, I was red on a couple of tests today. I need some extra sleep. So, so those are important tests to do. Absolutely. Yeah.
All right. Do we have any questions from the online audience, or are we wrapping up? All set? All right, wonderful. Now, I know we've got a gift for Megan. Thank you so much for doing this, Megan. This was truly wonderful.
Thank you, Dean Murthy.
Enjoyed it so much. You're really a role model for all of us, and we're so delighted that you're here, and so proud that you're a UCLA engineer. Join me in thanking you.
Thank you. Thanks for coming out.